In this video, we now want to look at how you can convert a galvanometer to an ammeter and how you can convert a galvanometer to a voltmeter. A galvanometer is a material that is used to detect a small amount of current. So of course, you know ammeter is used to measure current and voltmeter is used to measure what? Voltage, correct. So if you have a galvanometer, which in its design we know that it's used to detect just a small amount of current, small point of current, and you choose to convert it to an ammeter to measure current for you, or a voltmeter to measure voltage, what do you need to do? There are two materials we use, two resistance material. One is known as the shunt. The shunt is used to convert galvanometer to ammeter. Then we have the multiplier. And the multiplier is used to convert a galvanometer to what? A voltmeter. A shunt is a low resistance material. Is that okay? So it allows a large current to pass through it. You know, the lower the resistance, the higher what? The current. So it allows a high amount of current to flow through it and then a small quantity to pass through what? The galvanometer. Whereas a multiplier, like the name implies, to multiply, is that okay? It's a high resistance material. Hence, it allows only small currents to flow through it. During the connection, we connect a shunt in parallel with a galvanometer. You can see the diagram here. So that if you have total current entering, at this point, which is the principal junction, because two circuit elements are connected to that point, and those circuit elements, they have their resistances, their resistance values, right? So at this point, the current will divide. Recall that I told you that in the next class we're going to treat Kirchhoff's law, and so we'll learn about current division. Is that okay? Now the current is going to divide at this point. One will flow through the word shunt, and because shunt is a low resistance material, a large portion of this total current will pass through it, while a small portion will pass through the word galvanometer. Then we'll talk about the conversion of galvanometer to what? Voltmeter. In that case, a multiplier is connected in series with a galvanometer. So that if you have current here, is that okay? If you have total current here, since this is connected in series, and you know that a multiplier has high resistance, hence just a small portion of current will flow through it. And you know that when materials that have resistance are connected in series, the same current will flow through, is that not so? Which means that the small amount of current that will flow through the multiplier here as a result of its high resistance value, that small amount of current is what will flow through what? The galvanometer. Remember, galvanometer dictates small amount of current, a point of current, which means you want to do the connection in such a way that only a small quantity of current can pass through the galvanometer in each case. Do not forget, for galvanometer to ammeter, shunt is a low resistance material connected in parallel to the galvanometer, and then galvanometer to voltmeter, a multiplier which has a high resistance is connected in series with the galvanometer. In the next video, we're going to look at calculation of how we do this conversion to help us know the resistance value of the shunt and multiplier in these cases. In this video, let us look at a galvanometer that gives a full-scale deflection when a certain amount of current, 50 milliampere, flows through it. The resistance of the galvanometer is 5 ohms. How will you convert it to an ammeter capable of measuring 2 ampere? Do you understand the question? The resistance of the galvanometer is 5 ohms, alright? Now the galvanometer can only measure 50 milliampere current at full scale deflection. Now you're being required to determine how you can convert it to an ammeter capable of measuring a current of 2 amps. So how do we solve this problem? Already we have a sketch video in a previous video, so we can just still do something quickly. This is total current, okay, passing through it, and then let's say that this is our galvanometer, and then at this point we have to connect a shunt. You have to connect a shunt, so R shunt in parallel to the galvanometer. Is that okay? Something like this. So the total current is 2 amps, 2 ampere, And of course, the current that the galvanometer can measure, I galvanometer, let me say IG, is 50 milliampere. Alright, 50 milliampere. Milli is times 10 raised to power minus 3, which is the same as dividing something by 1000. So 50 divided by 1000 gives us 0.05 ampere. So this is the value of the current, is that okay, that the galvanometer can detect. This is what it can detect. So if we know that it's 0.05 ampere that the galvanometer can detect, the question now is, what happens to the excess current? Because the excess current cannot pass through it. If this excess amount of current passes through the galvanometer, it may destroy the galvanometer. Is that okay? Because the galvanometer shows full-scale deflection when 0.05 ampere passes through. So we're going to find a way to divert the excess current. Is that okay? We'll divert the excess current from the galvanometer. And to do that, we're going to use the shunt. Connect it in parallel like you see, so that the excess current will now divert and pass through the shunt. So I shunt, how do we get it? This is the total current 2 ampere that the ammeter can measure. Is that okay? Now, out of the total current, 0.05 is flowing through the galvanometer. So to get the one that is being diverted, it's going to be the total minus 0.05. That is, the I shunt will be equal to total current minus I galvanometer, right? So from here, we're going to get that our I shunt is equal to 2 minus 0.05. 2 minus 0.05. Let's see, that should be around 1.9 something, 0.05. Good, 1.95 ampere. So this is the current flowing through the shunt, this low resistance material. So what do we do now to calculate the resistance of this shunt? Because for us to convert this galvanometer to an ammeter, we need a shunt. So we need to find a material that has a certain value of what? Of resistance that can be able to divert that excess current through it. You don't just wake up and pick any material like that. You need to find out the exact material which is based on the resistance of that material. So let us do that. You know that when materials are connected in parallel, they have the same potential difference. Is that okay? So we're going to say that but the voltage across the galvanometer is equal to voltage across the shunt, because they are in parallel. Therefore, the current of the galvanometer times the resistance of the galvanometer, let's use small letter Rg, resistance of the galvanometer will be equal to current of the shunt times the resistance of the shunt. So we can substitute here and make resistance of the shunt subject to the formula, which is what we are looking for. That's going to be IgRg divided by what? Is. I think we can substitute now. We know the value of those terms on the right hand side. Current through the galvanometer is 0.05. We're going to multiply it by the resistance of the galvanometer. The resistance of the galvanometer is 5 ohms given. So I'm going to locate it somewhere. Our galvanometer is 5 ohms, alright? So I'm going to multiply by 5 and then divide by current through the shunt, which is 1.95. So if you do that, you notice that we need a material 0.05 times 5. So we're going to divide it by 1.95. So this is 0. Let's say 13 ohm. So we need a material of this low value of resistance. So this material can now divert this excess current of 1.95 through it. Is that okay? And allow only 0.05 ampere to go through the galvanometer. So the shunt we need is a material of this resistance, 0.13 ohms. In this video, we now have another question, alright, where it is desired to convert a galvanometer to a voltmeter capable of measuring voltages up to 20 volts. The galvanometer shows full-scale deflection when a current of 10 milliampere passes through it. If the resistance of the galvanometer is 5 ohms, how would you convert it to the required voltmeter? You see this, right? We want to convert a galvanometer to what? A voltmeter. So I'm going to ask you a question, alright? What do you need for this conversion? What do you have to say? Is it a shunt or a multiplier? That's very correct. A multiplier. Now tell us, the multiplier, is it going to be connected in series or in parallel to the galvanometer? In parallel? No. What do you say? in series. That's good. It's in series. For parallel connection, it's that of shunt, which we met previously in question 3. Is that okay? So here we're going to connect the multiplier in series with the galvanometer. I won't do a sketch here. Okay, to tell you that you can solve without even sketching. In the previous question, on that of shunt, we did a sketch. So what we need to know here is that the multiplier will be used. That is a high resistance material. And that the multiplier is meant to be connected in series with what? The galvanometer. So let us look at the data given to us from the question. The total voltage allowed here is 20 volts. Then the current of the galvanometer was given to us. It was stated in the question that the galvanometer shows full-scale deflection when a current of 10 milliamps flows through. 10 milliamps is the same as 0.01 amp. You divide it by 1000. Okay, then we have the resistance of the galvanometer, Rg, is given to be equal to 5 ohms. Okay, now we've identified that we need a multiplier for this connection. The next thing now is to determine the value of the resistance of that multiplier, so that we cannot just go and select any material, without knowing the resistance value. Now what do we do here? We need to know the base formula for this. Just like for the shunt calculation, when we're converting galvanometer to ammeter, the previous question, the base formula was that when materials in electric circuit are connected in parallel, they have the same voltage. Is that clear? Now, when materials are connected in series, what do they have? Is it the same voltage or the same current? That's very correct. It's the same current. So we can write, but for series connection, we expect that I galvanometer is equal to I multiplier. So we're not going to write this in terms of Ohm's law, which implies that V galvanometer divided by R galvanometer, I'm going to use small letter r here like we used there, is equal to V multiplier all over R multiplier. This is what we are looking for, R multiplier. So we would find a way to get Vg and V multiplier. We know the resistance of the galvanometer already. So how do we get the voltage of the galvanometer, being that we know its resistance? Take note that we know the current flowing through the galvanometer. The same current is flowing through the what? Multiplier. Can I say that? So take note of this equation, please. That's what we're going to use to solve our problem. So we can say, but V of the galvanometer is equal to current flowing through the galvanometer times the resistance of the galvanometer. And the current is 0.01 ampere. The resistance of the galvanometer is 5. So if we multiply this out, we'll notice that V of galvanometer should give us 0.05 volts. Is that okay? So this is V of the galvanometer. If this is the voltage of the galvanometer, we can now determine the voltage of the multiplier. Alright? Recall that total voltage will be equal to voltage of multiplier plus voltage of what? Galvanometer. Which implies that for the multiplier, the voltage will be voltage total minus voltage of the galvanometer. Is that okay? So the voltage of the multiplier will now be equal to total voltage is 20. Going to subtract voltage of the galvanometer, which is 0.05. This will give us voltage of the multiplier to be 20 minus 0.05. From here, it's 19.95 volts. Did you get the same thing? That's correct. So our problem is solved. We can now substitute into the equation now. Equation star. If you do that, voltage of the galvanometer, what's the value we got? That is 0.05. Resistance of the galvanometer is 5. So these things simply give us current. So it means I could have said that maybe I galvanometer, which is 0.01, is simply equal to V multiplier divided by what? R multiplier. Then I'll calculate my R multiplier. I see the relationship. Look at it. Ig, current through the galvanometer, equal to voltage of the multiplier divided by what? The resistance of the multiplier. So that's what we have here. So let's just substitute and see. Voltage of the multiplier, the value we got is 19.95. So I'm going to divide by R multiplier, which I don't know. If you work this out, your R multiplier, cross multiplying and dividing both sides by 0.05, you're going to have 5 times 19.95 all over 0.05. So we need a multiplier with resistance value. Let's multiply it and see, times 5 and then divided by 0.05. 1000, whoosh, this very high, 995 ohms. Are you not scared? So we need a material with resistance as high as 1995 in order to do this conversion. This material will block excess current, allow a little value of it to pass through it. And you know that because the multiplier is connected in series to the galvanometer, that same current, which is equal to 0.01, would now reach the galvanometer. Anything else this, the conversion will not be successful. In our previous class, we treated Ohm's law, which is one electrical law, very powerful, right, in determining current, voltage, or resistance in a circuit. One thing about Ohm's law is that it deals with a single circuit element, maybe like one resistor, or you can work around it and get maybe a combined resistor. Is that okay? Then you can use it to determine the current flowing in the circuit. Now, what if a situation where you have resistors connected in a form of network? We encounter such cases in circuit theorem. Is that okay? Where you could have resistors, they are connected, but these resistors, they are not parallel, they are not series. You see the connection, we refer to it as series parallel connection. Is that okay? Of the circuit element being a resistor in that case. We could also have inductors, you could have capacitors forming this circuit. So when they are connected in such a way that they are not in series, they are not in parallel, one might be required to determine the current flowing in a particular element. Does that make sense? The current flowing in what? In a particular element. Just think of a case where we have these parallel resistors. We've seen diagrams and that in our previous classes. And then imagine that you're asked to find the current flowing in a particular resistive element there. Do you recall that in our last class I stated that for parallel resistors, the current approaches a point called the principal node, a junction, alright, where the current will divide. So just imagine you are required to determine the current flowing in a particular element in such a case. You see? So it becomes necessary to extend Ohm's law to a case we can be able to still apply a related knowledge and solve to arrive at the required what? Answer. And that is why we introduce Kirchhoff's laws to physics in the study of circuits. There are two of them. Is that okay? One deals with the principle of conservation of charges, where we talk about the KCL, Kirchhoff's current law. And then the other, which is KVL, Kirchhoff's voltage law, is based on the principle of conservation of energy, because there we talk about the total potential rise and drop, is that okay, in a circuit being equal to 0. That's the algebraic sum. I know we're dealing with potential difference, dealing with voltage, it has relation to energy, as in energy function, is that okay? So it's actually a principle or a law based on the principle of what? Conservation of energy. Why that of current law is based on conservation of what? Charges. Good. Let us look at the laws now. KCL, the Kirchhoff's current law. It states simply that the total current entering a junction, a principal node, is equal to the total current leaving the junction. We have a sketch on the board here to help us get the idea of what we're talking about. You see, this is a junction, okay? It's a junction. You could see 3 currents entering that junction, that node, I1, I2, and I3. And then 2 currents leaving, I4 and I5. By Kirchhoff's current law, the sum of the current entering the node, which is I1 plus I2 plus I3, will be equal to the sum of current leaving, which is I4 plus what? I5. You could have more than this number of elements or even less than this. Is that okay? Now, if you walk around this equation, transfer this I4 and I5 to the left-hand side, for example, you'll notice that this will become summation of current in, and this will be summation of current out. Therefore, the sum of current, the algebraic sum, let's think about algebraic sum where you have plus and minus a term. All these terms are positive. These exit currents are what? Negative. So we can say the algebraic sum, putting them together, is that okay? Of the current will be equal to what? 0. Algebraic sum of current entering and leaving a node is equal to what? 0. So that is another way of stating it. If you don't want to say current entering is equal to current what? Leaving. I want to talk about KVL, the Kirchhoff's voltage law. It states that the algebraic sum of the potential changes encountered in a complete transverse loop circuit, is that okay? Is equal to what? 0. Now, in this definition, what we're really referring to is that the sum of the potential changes. You could have what we call potential rise and potential drop. You recall that for series connected elements, there are different voltages in them, is that not so? And now the total potential difference is produced by a cell that has a given EMF, like we learned before. So the total potential change or potential rise, which is produced by the EMF, the electromotive force by the cell itself, alright, is equal to the sum of the potential drops, of course, in the external circuit. When working with this KVL, in most cases, we do what we call loop transversing. The concept of transversing is not like it's anything difficult. Just select the direction you want current to flow. Like this, now if you look at, I've drawn this transverse in such a way that I am saying that current is coming out from this positive terminal. This is positive and then this is negative. Is that okay? This is anti-clockwise transverse. Someone might choose to say, okay, I'm transversing it in clockwise. So it means you're saying that current is coming out from the what? From the negative. I don't know if you get it. That's just your choice. Whatever sign convention you choose, you still arrive at the same result. This is the simplest form of it. You could still have maybe 2 or more loops connected, but the analysis is all the same. Get the potential rise and potential drop for each loop. If it contains 2 or more loops, you need to form a simultaneous equation which you have to solve to get the current in the circuit, perhaps in each loop as the case might be. In the next video, we're going to see how we apply this to solving problem. Let us look at this question. We have on the board here, we have to determine IA and IR in the figure below. And this is the figure, right? So how do we obtain the value of IA and the value of IR? We want to look at this. There are 2 junctions there, right? Look at one junction where current entered. We could see one leaving. Then this is another junction where these 2 currents, 1 ampere and IA, are leaving. But if you look at this arrow, from this IR is pointing in this direction, showing that this IR current is entering this node. Is that okay? So IR will be current entering this node here, whereas it is the current leaving this node. Is that okay? So what we need to do, we'll come to this point. Is that okay? We might choose to say that this is node A and this is node B. So we can say at node A, this current entering, that is 2 plus 3, these are the current entering, will be equal to the current leaving. And the current leaving is that IR. So let me indicate using KCL, Kirchhoff's current law. So you see that IR is equal to what? 5 ampere. So that's the value. Now let us move on to at node B. You notice that IR is entering. Is that okay? IR is entering. So that will be equal to the ones leaving. And the ones leaving are this 1 ampere and IA. Is that okay? So you see how we've written current entering equal to sum of current leaving, okay? This IR is entering this node B, and then current IA and current 1 ampere, they're leaving node B. So IR is equal to 5. We got that current already from here. So that will be 1 plus the current we're looking for, IA. Therefore, notice that IA is equal to 5 minus 1 ampere, which will give us what? 4 ampere. So that is how we calculate this using a KCL for a simple case like this. But though, even if you encounter it in a full circuit, it's still the same principle you apply. Check all current entering a particular node, make it equal to all current leaving that same node. We now want to look at the current divider rule CDR and the voltage divider rule VDR. You would recall that we had stated severally that a series arranged resistor, they serve as what? Voltage divider. Because the same current flows through them. What about the voltage? The voltage across series arranged resistors are different. When you now talk about parallel arranged resistor, what do we know about the current and voltage? Voltage in that case is the same, equal for parallel arranged what? Resistors. Now tell me, what about the current? Is the current the same? Not at all. They have different amount of what? Current. It was stated that at a particular junction, the total current produced by the cell, the source, we refer to the cell as a source, okay? Usually such term is used in a circuit theory. So the total current coming out from the source, once it reaches the junction where the resistors in parallel meet, that current will share according to the number of what? Resistors that are connected to that what? Junction. You recall all of those, right? Good. So we have these two diagrams on the board. This one is a parallel circuit, so it divides current. Is that okay? Why this is series circuit? You can see the resistors in series. So this one divides what? Voltage. Let's have maybe voltage here. This is a Vx. Is that okay? Then this Vy. Is that okay? Now, for this circuit, where the resistors are in parallel, one can determine the value of the current in each of the resistors. Please, I want us to take note of something, that this RY represents all resistors resolved to give us one single resistor. Is that okay? All resistors after this one. So, although I just showed one resistor here, we could have more than one resistor after this particular Rx. Is that okay? So when we resolve all the resistors to get the total resistors or resistance before this Rx, we can just replace it with what? Ry and draw it together with this in parallel. So how do we obtain the current flowing through this Rx, this resistance X? We write without proof the formula here on the board. Now we know that current is inversely proportional to what? Resistance. So applying the knowledge of Ohm's law, is that okay? We're going to have this equation that the current that is going to flow through this resistance X will be equal to, there will be an inverse proportion to each resistance. Is that okay? So the numerator here will be Ry, that is all other resistors ahead of it, divided by the total resistance, then multiplied by total current. Once we are able to determine Ix, we can now get Iy by subtracting Ix from I total. Please, this formula is very important, memorize it. Is that okay? Especially for anyone who studies circuit theorem, you encounter this a lot. There are some aspects of physics you can still use this and quickly get your result as well too, alright? To get the current in a particular circuit, if there is a concept of parallel resistor arrangement there. Now let us look at voltage divider rule that applies to what? To resistors in series. And once again, we write without proof that the voltage in the resistor Rx is equal to, you know that voltage is directly proportional to our resistance. So the Rx will be the numerator here. Are you getting me? When you are calculating Vx. Technically, in this case, we are calculating Ix because I is inversely proportional to our resistance. The resistance corresponding to which this current is flowing through was seen as a denominator, inverse relationship. But in this case, since voltage is directly proportional to resistance, then the resistance corresponding to this voltage will now be the numerator. Is that okay? Then all over Rx plus Ry. This is total resistance multiplied by what? The total voltage from the source. Once again, Ry here represents all resistors ahead of what? Rx. Once Vx is obtained, we can now determine the voltage in the resistor Y. Is that okay? So our Vy will now be V total minus what? Vx. we apply something like this when we're dealing with conversion of galvanometer to voltmeter. Is that so? We're going to see how we solve problems using this formula on the board. That we're going to see in the next video. Let us have some fun with this question on the board, okay? A battery of potential difference 6 volts is connected in a circuit to two resistances, 2 ohms and 3 ohm in parallel. So these two resistors are in parallel. Is that okay? The 2 and 3 ohm resistor. These resistors are connected in series with a 4 ohm resistor. We are asked to determine the total current in the circuit, the current through each of the resistors. You see, one might choose to sketch this if you want, but it's not necessary for solving the problem. Is that okay? I'm going to solve this problem without sketching it. So let us look at how it goes. First, we have this, that the potential difference, that is the total voltage in the circuit, is 6 volts. And then we have two resistors. Let's say R1 equal to 2 ohm, and then R2 equal to 3 ohm. Then let us say that R3 is equal to 4 ohms. And then R3 is in series with R1 and R2 together. Is that okay? This R4 is in series with R1 and R2 together. You can say that these resistors, that is 2 and 3 ohm resistors, are connected in series with the 4 ohms resistor. Now that we've made our analysis, we have to determine the total current in the circuit. To get the total current in the circuit, first you know total current is equal to total voltage divided by total resistance. So we need to calculate the total resistance in this circuit. Recall the 2 and 3 ohms are in what? Parallel. So we'll use the parallel formula. Is that okay? To determine the resistor or the value of the resistance of R1 and R2. So let me write. Okay, the first part of the question, current we don't know. But we know that current is equal to total voltage divided by what? Total resistance. And so I'm going to calculate the total resistance first. And to get the total resistance, it is going to be R12 plus R3. Is that okay? R12 will now be the parallel resultant resistance of R1 and R2. I can say that, but R12 is equal to, when you have resistors connected in parallel and there are only 2, you can quickly use this formula, multiply the resistance value divided by add the resistance value. Is that okay? So R12 will be equal to R1 times R2 divided by R1 plus R2. And that is now going to give us R1, R2 is what? That is 2 times 3 divided by 2 plus 3. If we work on this, 6 over 5 will give us 1.2 ohm. It implies that the total resistance, which is now R12 plus R3, will be equal to 1.2, because 1.2 is R12 we got already. Is that okay? We're going to add it to the R3 value, and R3 value is what? 4. Remember that these parallel resistors were connected in series with R3. That is why I wrote these two parallel, is that okay? Connected in series with this. And for series connected resistors, you add them straight ahead. Is that okay? While for parallel, you use reciprocal of the equivalent resistance equal to sum of the reciprocal of the others. Which I told you, if it is only two resistors, is that okay? To obtain the effective resistance, just do product of the resistance divided by sum of the resistance. You get it for parallel resistors. Is that okay? So let us do this. If you add these two, this is going to give us 5.2 ohms. So this is the total resistance in this circuit. It implies that current is equal to total voltage divided by total resistance, and the voltage is 6. We're going to divide it by total resistance, which is 5.2. Working on this, let's see what this is going to give to us. We have 6 divided by 5.2, and then we have 1.15 amps. So this is the total current, is that okay, in the circuit. We're going to take a short break. When we return from the short break, we are going to use current divider rule to calculate the current in each of the resistors. Very fast to do with the current divider rule formula. Is that okay? you're working from the short break. Now let us look at the second part of the question. In the second part of the question, we are to calculate the current through each of the resistors. Now we're going to use CDR here because of the fact that R1 and R2, which is 2 ohms and 3 ohms respectively, are connected in parallel. Now let me just give you a clue of what this diagram looks like. Is that okay? These circuits. You remember that this cell is being connected to two resistors rather. You can see this is your, let's say R2, then this is R1. Then these parallel resistors R1 and R2 were then connected in series with R3. So this is our 6 volts. You've seen what the connection looks like, right? So just imagine that current comes out of this cell, total current. On reaching this junction, it will split into 2. I1, then I2. Take note, they would move and then come over here, combine, and then pass through R3. Which means that the current that is going to flow through R3 is going to be I1 plus what? I2. You know that this current, they came out of the positive terminal. So they are trying to find their way to the negative terminal of the cell. That is how current moves, you know. We've treated that in our previous class. Current moves from what? The positive terminal, is that not so? And then it negotiates its way down to what? The negative terminal of the cell. So this is how they are moving. At this point, we will combine again this I1 and I2 to pass through what? R3. And then it will now move to the negative terminal of the cell. So at this point, we can actually apply CDR, current divider rule. So we're looking for, let's say we want to get I1 first, we don't know. So the formula using CDR, I1 will now be equal to R2 divided by R1 plus R2, then times I total. Just like we have the formula Ix equal to RY over Rx plus Ry, then everything times what? Total current. R2 here is representing Ry. R1 here is representing Rx. Good. Let us substitute and see. R2 was the value 3 ohms divided by R1 is 2 plus R2, which is 3. We're going to multiply by I total. Before the break, we already obtained I total to be 1.15 ampere. So I1 will now be equal to, let's see what that gives to us. That should be 3 over 5. You know, 2 plus 3 is 5, okay? We're going to multiply it by 1.15. If you do that, you get 0.69 ampere. So this is the current through R1. Is that okay? Current through what? R1. Then, we now want to obtain the next one. Let this be IIA. Then we're now looking at IIB. IIB. We want to get I2. We don't know. Again, we've gotten our total current. Since total current I total is equal to 1.15, and we know I1 to be equal to 0.69. We know that I total shared into I1 plus I2. Is that not so? I total shared into I1 plus what? I2. It implies that our I2 will now give us I total minus I1. Is that not so? And I total is 1.15, then minus I1 0.69. Good. So I2 will now be equal to, that is current through resistance 3 ohms here. Is that okay? Let's see what it gives to us. 1.15. We're going to subtract 0.69 from it. And from here, it's giving me 0.46 ampere. Good. Let's go to the last part of the question. So IIC. We want to get I through resistance of 4 ohms. Is that okay? The current through this. We represented it as R3 already. Is that not so? So I3 will be equal to I1 plus I2. I explained the reason from here. Since this parallel resistors together are connected in series with this R3. You know that for series resistors, the same current flows through them. So we want to get a total current that passes through these two resistors will now be the same current that will flow through R3. Is that okay? So that's what we have here. And that will be equal to I1. What did we get as I1? 0.69. You're going to add I2 to it, which is 0.46. Clearly, you would see that this is equal to I total because it is the I total that is shared at this point. So the same I total will move through there. If you do that, that is 1.15 ampere. Alright? So I'm going to indicate, note I3 is equal to I total here in this case. Is that okay? In this case. So that's how we resolve this problem. You can see how effective the current divider rule has proved to be in obtaining the current through each resistors quickly.